Ever just like stare out your window at a crazy thunderstorm and just kind of wonder how those swirling winds even get organized in the first place? Like we all know the basics, right? Like warm ocean, rising
Mm,
air, boom, hurricane.
right.
But what if I told you there might be like a deeper, more universal force at play here?
Yeah.
Like something that connects those tiny dust devils you see in a field to Jupiter's great red spot.
That's precisely what we're going to be exploring today.
Yeah.
We're diving into a fascinating scientific paper that proposes like a completely new way of understanding how storms form and how they stay around for so long.
Right.
It's called the SMFRVS theory, and let me tell you, it's pretty wild.
Okay, now I'm intrigued. So let's start with what we think we know. The usual explanation for hurricanes or typhoons goes something like this. Warm ocean water heats the air above it.
Right.
The air rises, creating an area of low pressure. And then the Earth's spin, that Coriolis effect, kicks in to get the whole thing swirling.
Yeah,
What's
yeah.
missing from that picture?
Well, the traditional explanation, I mean, it works well enough at a basic level, but it doesn't quite capture the whole picture. You know what I mean?
Yeah.
For instance, it doesn't explain why some energy inputs lead to these like beautifully organized rotating storms while others just create chaotic turbulence.
Right.
Why do we see those stunning spiral patterns, that fractal self-similar structure that's repeated across storms of all sizes?
Yeah, the good point. It's like nature is using the same blueprint for a tiny dust devil in a field and a massive hurricane spanning hundreds of miles. There's got to be a deeper connection there.
That's where the SMFRVS theory steps in. It proposes that the atmosphere isn't just like an empty space where winds just blow around randomly. It's actually permeated by a subtle energy field, a sort of cosmic lattice that influences how energy flows and how it organizes itself.
A cosmic lattice. Okay, now you've really got my attention. What exactly does that mean? Is it like some invisible force field holding the atmosphere together?
You can think of it as like a vast interconnected network, almost like a giant web spanning the entire atmosphere. And this web is influenced by two key factors: the subtle magnetic field, or SMF, and the relative vacuum of space, the RVS.
Hold on. Space is a vacuum. I mean, we all learned that in grade school. So how does that play into things down here at ground level?
It's more about the interaction between the vacuum of space and the atmosphere. Think of it this way. The atmosphere is constantly trying to equalize pressure differences with the vacuum above it, and this creates a subtle but ever-present tension.
Okay, so we've got this cosmic lattice, this invisible web of energy spanning the atmosphere, and there's a constant push and pull between the atmosphere and the vacuum of space. How does that actually create a storm?
That's where things get really interesting. This tension between the atmosphere and space, combined with the influence of the subtle magnetic field, creates what the SMF-RVS theory calls a push wave. It's like a ripple that travels through the lattice, carrying energy with it.
So like a wave on the ocean, but this one's rippling through this invisible energy field.
Exactly. Now, according to the SMF-RVS theory, the heat energy from warm ocean water doesn't just passively warm the air above it, it actually acts as a booster for this push wave, amplifying its strength in specific areas.
So the warm ocean isn't the cause of the storm. It's more like it's giving an extra kick to this already existing waves of energy.
Precisely. Think of it like adding fuel to a fire. The fire was already burning, but the fuel makes it burn hotter and brighter.
Okay.
And here's where things get really mind-blowing. As this boosted push wave ripples through the cosmic lattice, it eventually reaches a point where it becomes unstable.
Unstable how? What happens then?
This instability creates a feedback loop. Instead of just dissipating, the energy in the wave gets locked in and the wave starts rotating, forming that classic swirling vortex we see in hurricanes and typhoons. It's like a spinning top finding its balance. It starts wobbling, but then it locks into a stable spin.
So the Earth's spin is still playing a role, but it's not the driving force. It's more like it's guiding the direction of that spin once the energy gets locked in.
You got it. Now, what's truly fascinating is that the SMF-RVS theory goes even further. It proposes that there are two fundamental scaling constants built into this cosmic lattice, kind of like universal laws that govern how this push wave behaves.
Wait, scaling constants, what are those and what do they have to do with storms?
These constants, well, they essentially dictate how the wave patterns repeat across different sizes. They ensure that the structure of the storm, that fractal pattern we talked about, remains consistent whether it's a tiny dust devil or a massive hurricane.
So it's like a set of rules embedded in the fabric of the atmosphere itself that ensure storms form and behave in a predictable way, regardless of their size.
You're getting it. And that's where the traditional explanation starts to fall short. It struggles to explain why we see this consistent structure across such a vast range of scales. But in the SMF-RVS framework, it's a natural consequence of these underlying scaling constants. Pretty neat, huh?
It's like we've stumbled upon a hidden code that governs weather patterns, from the smallest gust of wind to the largest hurricanes. But if this SMF-RVS theory is so groundbreaking, does that mean everything we thought we knew about storms is wrong?
Not entirely. It's more like the SMF-RVS theory adds a deeper layer of understanding. The traditional factors we talked about, warm water, rising air, the Coriolis effect, those are still important, but they're acting on top of this more fundamental push wave system.
Okay, so it's like we've been looking at the leaves on a tree, and now we're starting to understand the roots and the trunk that support them. This is getting really fascinating. But I have to ask, how does all of this explain something like Jupiter's Great Red Spot? That storm has been raging for centuries. I mean, it defies all our conventional explanations for how storms form and how they die out.
Ah, that's where this theory gets even more exciting. We'll dive into the mysteries of Jupiter's Great Red Spot in the next part of our deep dive.
All right, listeners, we're about to take this cosmic journey to another planet. You won't want to miss it. Stay tuned for part 2.
Welcome back to our deep dive into the SMF-RVS theory.
I am ready to journey to Jupiter. Last time, we left off with this really intriguing idea of a cosmic lattice and a push wave that might be like the hidden forces behind storm formation. But how does all of this explain something as mind-boggling as Jupiter's Great Red Spot? I mean, that storm is bigger than Earth itself, and it's been swirling for centuries, maybe even millennia.
Yeah, it's a truly awe-inspiring phenomenon. And you're right, it challenges our conventional understanding of how storms work. I mean, the traditional explanation suggests that storms, especially ones that massive, should eventually just run out of steam due to friction and break down into turbulence. Yet the Great Red Spot persists. It's almost like a perpetual motion machine.
So how does SMF-RVS help us make sense of this seemingly eternal storm?
Well, remember that cosmic lattice we talked about, that vast network of energy that permeates the atmosphere? Well, on Jupiter, this lattice is on a scale that dwarfs anything we see on Earth. Jupiter's immense size, its rapid rotation, and its powerful internal heat engine all contribute to a supercharged version of that SMF-RVS push wave that we discussed earlier.
So it's like Earth's push wave, but on steroids.
Exactly. Now imagine this incredibly powerful push wave interacting with all the dynamic forces at play in Jupiter's atmosphere. Energy bubbling up from its interior, different layers of gases shearing against each other, and even the gravitational pull of its many moons.
Wow.
These interactions, they create disturbances, and these disturbances are where things get really interesting.
Okay, I'm picturing this giant push wave sweeping through Jupiter's atmosphere, and these disturbances are like ripples forming on its surface. What happens to those ripples?
Instead of just dissipating or creating random turbulence, these ripples, under the influence of the SMF-RVS push wave and those universal scaling constants we talked about, actually form these stable ring-shaped structures. Think of them like miniature whirlpools within the larger flow of the atmosphere.
So we have these tiny organized whirlpools embedded within this massive push wave. How does that translate to the Great Red Spot, which is anything but tiny?
Well, the Great Red Spot, according to the SMF-RVS theory, is essentially a region where a collection of these ring-shaped structures has become incredibly stable and self-reinforcing. The powerful push wave constantly feeds energy into them, maintaining their swirling motion.
So the Great Red Spot isn't just one giant vortex. It's more like a cluster of smaller vortices all swirling together in a synchronized dance.
That's a great way to visualize it. And remember those fractal scaling laws we discussed earlier?
Mm-hmm.
Well, those laws ensure that the overall structure of the Great Red Spot, that distinctive swirling pattern, remains coherent and resists breaking down into chaotic turbulence even over centuries.
So it's like Jupiter's atmosphere has found a way to channel all that energy into this incredibly stable and long-lasting structure. But that raises another question. If the SMF's RVS theory can explain the Great Red Spot on Jupiter, why don't we see storms lasting that long here on Earth? We have warm oceans, we have the Coriolis effect, we even have those scaling constants, right?
You're right, the ingredients are all there, but there are some crucial differences between Earth and Jupiter that affect how the SMF-RVS system plays out. Let's head back to Earth for part 3 of our deep dive to explore those differences.
I can't wait to find out why our storms are so fleeting compared to the cosmic ballet happening on Jupiter. Don't go anywhere, listeners. We'll be right back. Okay, so we're back for the final part of our deep dive into storms. And wow, we've just taken a whirlwind tour of Jupiter's Great Red Spot. Talk about an epic storm. But you know what makes you wonder why Earth's storms, even those powerful hurricanes, seem so, I don't know, so short-lived in comparison? What's the difference?
Well, it all comes down to scale, energy, and the very nature of the atmospheres on these two planets. Remember that cosmic lattice we've been talking about? On Jupiter, well, it's like having a vast, uninterrupted dance floor for that SMF RVS push wave to sweep across.
So you're saying Jupiter's atmosphere is like a giant, smooth surface, perfect for those stable, ring-shaped structures to form and just keep swirling for centuries.
Precisely. Jupiter's atmosphere is essentially one giant swirling ocean of gas, thousands of miles deep with no continents or mountains to break up the flow. This allows that push wave to create like a stable and incredibly vast fractal lattice, the kind that can support a storm like the Great Red Spot for millennia.
But here on Earth, it's like trying to dance in a crowded room full of furniture, right? We've got continents breaking up the flow, mountains creating turbulence, and a much thinner atmosphere overall.
Exactly. All those obstacles disrupt the formation of a large-scale, stable fractal lattice, like the one we see on Jupiter. It's harder for those ring-shaped structures to form and lock into those long-lasting patterns because they're constantly bumping into things, so to speak.
So the push wave on Earth is like a dancer trying to waltz in a mosh pit. Good luck with that. But isn't it also about how much energy is feeding into the system? Jupiter's a giant ball of churning gas and heat, right?
That's another crucial difference. Jupiter's internal heat and rapid rotation pump a tremendous amount of energy into its atmosphere, constantly fueling the SMF RVS system. And because this energy is spread out over such a vast area, that push wave is just incredibly powerful and stable.
It's like having a giant furnace constantly stoking the fires of those swirling storms. But on Earth, our energy input is much smaller and more localized, isn't it?
Exactly. Most of the energy driving Earth's storms comes from the heat in our oceans, which is concentrated in specific areas. So while a hurricane might get a big energy boost when it passes over a warm patch of ocean, it starts to lose energy pretty quickly as it moves over cooler water or encounters friction from land masses.
So it's like trying to keep a bonfire going with a few twigs compared to Jupiter's raging inferno. Our storms are basically fighting an uphill battle right from the start.
And there's one more factor to consider. Earth's atmosphere is simply more chaotic and turbulent than Jupiter's. I mean, we have jet streams, weather fronts, all sorts of things constantly changing the local conditions, which means that the SMF RVS push wave is also constantly changing, making it harder for storms to lock into those stable, long-lasting patterns.
So even if a storm on Earth manages to tap into that push wave and form a vortex, it's kind of at the mercy of all these other forces swirling around it. No wonder our storms are so much more unpredictable.
It's like trying to build a sandcastle on a windy beach. You might get a nice structure for a little while, but the wind and waves are constantly working against you.
This has been an incredible deep dive. We've gone from like those familiar explanations of hurricanes to these really mind-bending concepts like cosmic lattices and push waves. It's amazing to think that there might be this hidden energy field shaping the weather all around us.
And remember, this SMF RVS theory is still relatively new, but it offers a fascinating glimpse into the deeper forces at play in our atmosphere. Who knows what other mysteries it might help us unlock in the future?
Yeah. Maybe one day we'll be able to use this knowledge to predict the paths and intensity of storms with, I don't know, much greater accuracy, potentially saving lives and resources.
Indeed. It highlights the interconnectedness of everything on our planet and beyond. From the smallest gust of wind to the grand swirling storms on Jupiter, it's all connected.
That's a truly inspiring thought to end on. Thanks for joining us on this deep dive, listeners. Until next time, keep looking up, keep exploring, and never stop wondering about the world around us.